Hi. In this video, we are going to look at some interesting results proven by Euler. This we are going to talk about the gamma function and an amazing formula, which is the formula for sine y in the form of an infinite product. And finally, the reflection formula for factorials, which basically extends the concept of factorials from positive to negative factorials. And we can find the value of some weird factorials, basically. The idea for this video is from a video by Michael Penn, which was uploaded, I think, a couple of days ago, where he talked about Euler's other constant, which is the Euler-Mascheroni constant, right? Which is the difference between the harmonic function and the value of the log function, which approximates it as n tends to infinity. So that is going to be useful in our discussion here. And let's get started. I'm sure many of you will appreciate the final results that we will show here in this video. These are quite stunning and the formulas are beautiful. So hopefully you'll enjoy what we will present here. So first of all, we begin with the gamma function, and the gamma function is defined like this. So tau of n is equal to integral 0 to infinity e power minus x multiplied by x power n minus 1 dx. And this is true for n greater than 0, right? Now, for example, for n is equal to 1, you can evaluate this. For n is equal to 1, let's find the value of this. So tau of 1 will become 0 to infinity e power minus x dx. And that comes out to be simply 1. You can calculate this integral pretty easily. Now, what we want to do is we want to extend the idea of factorial function from non-negative integers to all real numbers. But first of all, you need to understand why this integral is related to the factorial idea, right? So we can show that by simple integration by parts. So if I have this integral, this is point number 2. So if I have tau of n like this, 0 to infinity e power minus x, x power n minus 1 dx, then obviously I can do by parts integration on this term, and that will become e power minus x. I am integrating this. So my first function is e power minus x, second function is integrated. So that becomes x power n by n. Limits are 0 to infinity minus, then we have 0 to infinity minus of e power minus x, which is differentiating the first function and keeping the answer here as it is, x power n by n dx, right? So this is when you integrate by parts here. What are we getting? When you put the limits infinity here, e power minus x vanishes. And when you put 0, x power n vanishes. So this whole part just disappears. And then finally you have plus of 1 by n, 0 to infinity, e power minus x, x power n dx, right? So if you think about it, that is tau of n plus 1, right? So this part is basically tau of n plus 1 and 1 by n, right? So that gives us a nice result. And I'll write this result in the next screen. So the result is tau of n plus 1 by n is equal to tau of n. We just now proved it by integrating by parts the integral for tau of n, right? So that implies that tau of n plus 1 is equal to n times tau of n. And this is a typical property of factorial. So we can basically say tau of 2 is equal to 2 times tau of 1, which is 2 times 1, which is 2 factorial. Similarly, tau of 3 is 2 factorial, and so on. So we get basically the property that tau of n is equal to n minus 1 factorial, right? Correct. This definition looks like a factorial definition for n is an integer. But if you recall, the tau of n function was an integral. It doesn't assume that n is an integer, right? Here, we don't assume that n is an integer. So tau of n is a more general result which is valid not just for n and integer, right? So the idea is that maybe now we can find things like tau of half, right? Tau of half basically would be, according to this formula, it should be minus half factorial. So in some sense, we will be able to find out minus half factorial if I put n is equal to half in this integral, right? So can we just try it out and figure this out? So this is 0 to infinity e power minus x. And when I put n is equal to half here, it becomes x power minus half dx. So that is basically 0 to infinity e power minus x by root x dx, right? So I'm going to try to find minus half factorial, right? So minus half factorial has been defined in terms of my gamma function when n is equal to half, because the gamma function does not have a restriction on n, right? N could be an integer, n could be rational, n could be negative, whatever, right? So now we are trying to evaluate minus half factorial and we get this integral. This is pretty easy to solve. Like we'll do it here. We say tau of minus half, or tau of actually half, tau of half is equal to minus half factorial. Here we use the fact that tau of n is equal to n minus 1 factorial. And we are saying minus half factorial is equal to integral 0 to infinity e power minus x by root x dx, right? How do I evaluate this integral? I do a simple change of variable. X is equal to t square. So dx should be equal to 2t dt. And if x is equal to t square, the limits remain unchanged. So it is 0 to infinity e power minus t square by root x is t. And this becomes dx becomes 2t dt. So t and t gets cancelled, and this is basically twice of 0 to infinity e power minus t square dt, right? Correct? So basically now if I know this integral e power minus t square 0 to infinity dt, then I will know the value of minus half factorial, because that will be double of that, right? Now this integral is known as a Gaussian integral, and it is a very famous integral in many higher level mathematics courses. You will encounter this, especially in probability and statistics. We have recently made a video on this Gaussian integral, and I have proven that this is equal to root pi by 2. So that is a standard answer. You can check out my previous video on this integral. So once we get this, we are basically getting root pi by 2 for this. So now we can put that answer here and we get minus half factorial is equal to twice of root pi by 2. And basically we are getting it as root pi, right? So minus half factorial is coming out as root pi, which is a surprising identity. However, it is true in this sense, right? Because we have derived it from identities that were coming out to be true. And we have basically just evaluated the integral that gives us the gamma function, right? Now, in the equation where we wrote tau of n is equal to n minus 1 factorial, in that equation, we can replace it with even more weird things. We can replace n with 1 minus n, right? So let's see what comes from there. We have this result. Now we go ahead and see what other conclusions we can derive. So our equation was tau of n was n minus 1 factorial. And let's replace n with 1 minus n here, right? So that becomes tau of 1 minus n becomes 1 minus n minus 1 whole factorial. So that is basically minus n factorial, right? Tau of 1 minus n is equal to minus n factorial is coming, right? So we can say that tau of n, so if I say n times tau of n, that will become n times n minus 1 factorial. That is simply n factorial. So if I take this result and multiply it with this result, so I'll get n times tau of n multiplied by tau of 1 minus n should be equal to n factorial and minus n factorial, right? Correct? So if this is actually the reflection formula that I was talking about earlier. However, right now, if you want to evaluate minus n factorial, you need to find the values of these integrals, right? Tau of n and tau of 1 minus n are actually integrals. And we already know n factorial. So if you want minus n factorial, you should be able to figure out the LHS of this, right? So we can basically have a method of finding minus n factorial, given that you are willing to calculate the integrals here, right? Tau of 1 by n by n factorial, right? So this is your expression, and the reflection formula basically gives us a way to define negative factorials in this way, right? However, we want to do a little bit of an aside here and derive another surprising and shocking way to show us this reflection formula, which involves sine functions. So that is surprising because this doesn't look like it will ever have sine, any connection to the sine function. So what I'll start with here is I'll try to prove the infinite product for sine that was derived first by Euler here. So we will come back to the tau function and the gamma function later. We'll first take a brief aside where we try to understand how Euler came up with this result. Sine y was expressed as y into product from n is 1 to infinity and the infinite product of 1 minus y square by n square pi square, right? Now, this looks very weird. It is strange. And basically, if I expand and write a few terms, you will understand what is happening here. So this is 1 minus y square by pi square. And then it will be 1 minus y square by 2 square pi square. And so on, so on. 1 minus y square by 3 square pi square. And this is an infinite product, right? What I want to understand is the intuition behind this expansion, okay? Because later we'll connect it to the gamma function, right? So obviously the process that we are going to follow to sort of understand this is not very mathematically rigorous, but it is very intuitive. And I think all of you will be able to appreciate what Euler did. What Euler did in the late 1800s, 18th century was not always mathematically rigorous by the standards that we have today for analysis, but it was deeply fundamental and it was surprising and beautiful all the same. And the way he discovered these things, people have later come up with rigorous proofs to show all of these, right? What we will follow is the slightly less rigorous but more intuitive way of understanding this product, and in the sort of fashion that Euler did it himself, right? So what you will see here is, in order to understand this, we'll start with the power series expansion for sine y. And sine y is y minus y cube by 3 factorial. This I think everybody is familiar with. This is the Taylor series expansion for sine y near 0, right? Now from here we can say sine y by y is becoming 1 minus y square by 3 factorial plus y power 4 by 5 factorial and so on, right? So sine y by y is coming out to be this infinite series, right? Now think about this. The right hand side of this equality is basically a polynomial, but in some sense this is a polynomial of infinite degree, right? Why is it a polynomial of infinite degree? Because technically the powers of y are going to keep rising, right? And it has only even powers, right? It has even powers and infinite degree, right? Now think about it. If you have a polynomial py of degree s, py of degree s with non-zero roots, and the roots are r1, r2 till rs, right? Then we could have written py as some a times y minus r1 multiplied by y minus r2 and so on till y minus rs, right? This is true for any general polynomial of degree s as long as you have r1 to r2 till rs distinct roots. We can always write py like this, right? We have a coefficient, some constant, and then expressing the py as a product of factors, right? Great. So if it is written like this, we could take -1 common from each of these factors and multiply it with the a and write it whatever it comes. Basically, it could come -1 or it could come +1. We are taking -1 common from each factor, multiplying it with the outside constant. Here a was a constant, so we can now call it b and write it as r1 minus y, r2 minus y, and so on from till rs minus y, right? So basically, we are writing py as b times this, right? Great. Now, the next step is to think of py as b times. Take r1, r2, r3 common, r1, r2, r3 common from each of the factors till rs, and you'll get 1 minus y by r1 into 1 minus y by r2, and so on till 1 minus y by rs, right? So we can now combine this b with these r1, r2, r3, rs and call it another factor, and let's call it a again, some constant a. This is some constant. I don't care about the value of the constant at this stage. It is just the product of b and everything else, all of these roots, right? So a into 1 minus r1 y by r1 into 1 minus y by r2. This is a valid expression for the polynomial p, right? Py. Correct? Now, what Euler said is he knows that sine y can be 0 and sine y has roots n pi, where n can be 0 or plus minus 1 or plus minus 2 and so on, right? But sine y by y equal to 0 has roots basically n pi, where n cannot be 0, right? Because you cannot put denominator 0 here, right? So sine y by y equal to 0, that equation will have roots n pi, right? Great. And we already know that sine y by y is an infinite polynomial with this type of nature, right? We have taken the Taylor series expansion and we have this as the infinite polynomial. It has only even powers. So technically, this sine y by y is a polynomial in y square, right? Since it has only even powers, we can think of this as a polynomial in y square, right? Because this expression can be written as a function of y square, right? So if we have a p of y square equal to 0, sine y by y is a polynomial in y square. So p of y square is equal to 0. This equation will have some roots, right? This equation will have roots which will be the square of the roots of p of y, right? P of y was this. Those roots were n pi. So p of y square's roots will be n square pi square, where n is not 0, right? I hope everybody is understanding what I'm saying here. Because sine y by y equal to 0 has roots n pi equal, where n is not equal to 0, and sine y by y was thought of as the polynomial py. But we can think that this py is technically a polynomial in y square, right? Because it only has even powers, right? So we can write this p of y square as p of y square is equal to 0 has roots n pi whole square, right? N pi square, where n can be plus minus 1, plus minus 2 and so on, correct? So if that is true, then we can write the p of y square as some constant into 1 minus y square by all the roots, right? 1 minus y square by 1 pi square into 1 minus y square by 2 square pi square and so on, right? Why? Because earlier we saw that any polynomial py can be written as a times 1 minus y by r1, 1 minus y by r2 and so on, right? So right now, instead of y, I have y square, and instead of the roots, I have the pi, n square pi square roots, right? So basically, finally, what we are saying here is that sine y by y can be written as a times 1 minus y square by pi square, 1 minus y square by 2 square pi square, and so on as an infinite product, because the number of roots are infinite and roots are n pi whole square, right? Great. If you take the limit of the LHS as y tends to 0, sine y by y, this tends to 1. And if you take the limit on this side, you will realize that each of the factors tends to 1 when y tends to 0. And therefore, a is the limit here. So a must be equal to 1, right? So in this way, Euler concluded that sine y by y is equal to 1 minus y square by pi square, 1 minus y square by 2 square pi square, and so on, right? This infinite product. So that is your Euler's infinite product expansion for sine y. So sine y can be written as y times this. Now, this looks amazing and this looks weird. And also it has some interesting applications. So I will show you one small bonus application here. So for example, now I have sine y by y is equal to 1 minus y square by pi square, 1 minus y square by 2 square pi square, and so on, 1 minus y square by 3 square pi square. Let's see this, and we write the Taylor series expansion on this side for sine y by y. That was y minus y cube by 3 factorial plus y power 5. This is the Taylor series expansion for sine y, and that should be equal to, this is infinite series here, should be equal to y times this, right? Y times this. Great. So what is the benefit now? What we can say is, can we think of the terms here? The first term will be, all the ones will multiply with themselves, and that will multiply with y. So you'll have a y here, and then all the pi square terms will multiply with the other constant. So we'll have one term which will look like this: 1 by pi square plus 1 by 2 square pi square plus 1 by 3 square pi square, and so on till y cube. Basically, I am collecting all the terms that will have power y cube here. How will you get y cube term here? There are so many factors, right? There are so many factors. Each factor has a y square term. If you multiply the y square term with this y, and all the other factors you choose 1, right? Since from every factor here I choose 1, and from one of the factors I multiply with the y square term, I will get a minus y cube, right? So I'll get a minus y cube by 3 square pi square term. Similarly, I'll get a minus y cube by 3 pi square term. So basically, I'm saying I'm collecting all the terms with this, right? I'm basically finding the coefficient of y cube in this expansion. Obviously, there are many other terms in the series, right? There will be coefficients of y power 4 and so on, so on. Those will be slightly more annoying to find, because then we'll have to group two terms together and so on, right? But right now, what I want and what I'm interested in is the coefficient of y power 3 here in this expansion, right? Because this side also I have a Taylor series expansion, which is an infinite series, and this side also I have an infinite series. So I can obviously equate the coefficients, right? Notice that the first term is matching. And so I should be able to equate the coefficients, and I should say that minus 1 by 3 factorial should be equal to this, right? So I'm getting this nice result, minus 1 by 3 factorial is equal to minus of 1 by pi square plus 1 by 2 square pi square and plus 1 by 3 square pi square and so on till infinity. And this basically becomes, pi square can be taken this side. So pi square by 3 factorial is equal to, now we are getting 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on. And basically this is the Basel problem. This was a problem that Euler solved much before he proved this infinite series expansion, but he became famous for solving this series, finding a closed form expansion solution for 1 by 1 square plus 1 by 2 square and so on. And this is pi square by 3 factorial, which is pi square by 6. So from the infinite series expansion, we are able to derive a known formula, right? So that gives us that tells us that the expansion might actually be correct, right? Even though it is hard to believe that this can be true, the expansion might actually be correct, right? Because we are getting the correct answer for the Basel problem from this expansion, right? Anyway, that was just a simple application of the formula that Euler derived. The next part of the video, we are going to talk about the reflection formula and how we can figure out an actual closed form method to find n factorial and minus n factorial, and that involves the sine function. So let's go with this. Let's see, n factorial can be written as 1, 2 multiplied by n minus 1 till n, right? We want an expression that makes sense even when n is not an integer, and n can even be negative, right? So suppose alpha is another integer, right? Alpha is another integer, and we will eventually say alpha tends to infinity. So the exact value of alpha doesn't matter, because eventually we'll say limit alpha tends to infinity. So now we can write this as n factorial is equal to limit of alpha tends to infinity, and I will write it like this. This becomes 1 into 2 into 3 till n minus 1 into n in brackets, and then I'll multiply it with, I will remove this off here. I'll multiply this with n plus 1, n plus 2, so on till n plus alpha multiplied by alpha power n by n plus 1 by the same thing, because we obviously have to multiply and divide by the same quantity, right? Okay, so if I do this right now, correct? Then let's manipulate it a little bit. We will get here limit of alpha tends to infinity, n factorial is equal to this. And now what we say is we collect all the terms here till n minus 1, n, then n plus 1 till alpha. Okay. And in the denominator, we again say n plus 1, n plus 2, n plus alpha. And the remaining terms are alpha plus 1, alpha plus 2, till n plus alpha. And we have alpha power n here divided by alpha power n. This is just a restatement of the original thing only. It's nothing different. But now what we can do here is we can write this as alpha factorial into alpha power n. Alpha power n was here. And we are dividing it by n plus 1, n plus 2 till n plus alpha. And we are multiplying it with alpha plus 1, alpha plus 2, and so on till n plus alpha by alpha power n, right? Great. And the whole thing is taken as limit alpha tends to infinity, right? Okay, so this is n factorial is equal to this. We have done nothing major so far. We have just rewritten the terms, included alpha, and we have rearranged it to make it look like this, right? Now, what is the benefit of all this? We can first of all realize that all the terms here will have limit 1 when alpha tends to infinity, because we can say alpha plus 1 by alpha, alpha plus 2 by alpha, and so on, alpha plus n by alpha. When alpha tends to infinity, this is 1 plus 1 by alpha, 1 plus 2 by alpha, and finally 1 plus n by alpha. All of these terms tend to 1, tend to 1, tend to 1, right? So this whole part will tend to 1. So we can technically remove that here, and our final n factorial is still going to be equal to limit of alpha into alpha power n by this expression, right? Awesome. So now here, what I will do, I'll take n common in each of the fractions here. So it will become alpha factorial, alpha power n, and n common in each of the factors. So what I will get here is n. Actually, I should take n common in each of the factors. There are alpha factors, right? So 1 plus n by 2. Okay, I will rewrite it like this: 1 plus n by 1. No, I am not taking n common actually. I'm saying 1 common from the first one and 2 common from the next one. So it will become 1 plus n by 2 and 3 common from the next one. So that will be 1 plus n by 3. And finally, alpha common from the last one, and that will be 1 plus n by alpha, right? So in the denominator, you can see 1, 2, 3 till alpha comes, which is basically alpha factorial. So gets cancelled from the top, right? So finally, you have limit alpha tends to infinity alpha power n by the product of these factors, right? Great. So I will rewrite it on the next screen. So we have n factorial is equal to limit of alpha tends to infinity, and we have cancelled the alpha factorial from top and bottom, and we have alpha power n by 1 plus n by 1, 1 plus n by 2, and so on till 1 plus n by alpha, right? Great. So we have this result now, and what we do here is we write alpha power n as e power ln alpha power n, which becomes e power n ln alpha, right? This is a standard transformation. And now we recall the Euler's constant, which is equal to limit of alpha tends to 0 the alpha tends to infinity, h of alpha minus ln alpha, right? Where h of alpha was 1 plus 1 by 2 plus 1 by 3 and so on till 1 by alpha. This is the harmonic series and this is the ln x function which approximates the harmonic series, and gamma is the difference between this and this. And I would direct you to Michael Penn's video yesterday where he was describing this in great detail. I think this constant will be useful in our derivation as well, and you should look at his video. It is great. It's a very good exposition. So now what I will do here is ln gamma is going to be equal to, actually not ln gamma, I will not write ln gamma, I will say this limit, right? Gamma is equal to limit of alpha tends to infinity h of alpha minus ln alpha, right? So we can say that ln alpha is equal to minus gamma plus summation of k goes from 1 to alpha 1 by k. Basically, this is h of alpha. This is my harmonic series. H of alpha is like find the total sum of the harmonic series and subtract ln alpha, that is gamma. So ln alpha is obviously negative of gamma plus the harmonic series from 1 to alpha, right? Correct. And as alpha tends to infinity here, that is the condition in which this is true, right? So what we can say is ln alpha is minus gamma plus 1 plus 1 by 2 plus 1 by 3 till 1 by alpha as alpha tends to infinity, right? Okay. So this is going to be useful here. The gamma factor, the gamma constant is something that you need to be aware of what it really means. It is the difference between the infinite harmonic series and the ln x function, right? So we are just saying ln alpha is minus of gamma plus this, right? You can transpose it to this side and write it in this side, and that becomes the definition of the gamma constant, right? So we have not done anything weird here. We are just trying to write ln alpha in this way, right? Because we will be using it here, okay? So if ln alpha is this, right? Then e power n ln alpha, e power n ln alpha will become e power n minus gamma plus 1 plus 1 by 2 plus 1 by 3 and so on till 1 by alpha. And this is when alpha tends to infinity, right? So therefore alpha power n becomes e power minus n gamma multiplied by e power n multiplied by e power n by 2 multiplied by e power n by 3 and so on till e power n by alpha, right? If you take all the powers and add up all the powers, you'll get the top expression, right? Great. So the earlier expression that we had was n factorial was equal to limit and alpha tends to infinity alpha power n by 1 plus n by 1, 1 plus n by 2, and so on till 1 plus n by alpha, right? This was the expression we had earlier, and now we replace alpha power n with what we have derived using the gamma constant, and we get e power minus n gamma, e power n by 2, and so on till e power n by alpha divided by 1 plus n by 1, 1 plus n by 2, and so on till 1 plus n by alpha, right? And we have limit of n tends to infinity, alpha tends to infinity, right? So now think about it. You already know there is a standard limit e power x by 1 plus x, limit x tends to 0. That limit is 1, right? So, okay, but right now the x is not tending to 1, x is n actually. So we have to be a little careful here. So I will do one more step here. So I'm getting n factorial is equal to this, right? Great. I will rewrite it on the other screen. N factorial is equal to, I am getting e power minus n gamma and limit of alpha tends to infinity e power n by 1 plus n by 1 and e power n by 2 and 1 plus n by 2 and so on till e power n by alpha and 1 plus n by alpha. This is what I have gotten in the previous screen, right? So if I replace this with minus n factorial now, I'll get e power n gamma limit of alpha tends to infinity. And this time I'll get e power minus n by 1 minus n by 1. And e power minus n by 2 and 1 minus n by 2, right? And so on till e power minus n by alpha by 1 minus n by alpha, right? Why are we doing this? We are doing this because ultimately I want to get n factorial into minus n factorial, right? We had seen earlier that that was n tau of n into tau of 1 minus n. This was something that we derived earlier in this video when we were talking about gamma functions, right? So now I want to get the product of these two. And if you see the product here, n factorial into minus n factorial is becoming basically this part just cancels out, right? And it is becoming limit of alpha tends to infinity. And product of this will be what? The top part will vanish, e power n and e power this. It will become 1 by 1 minus n square by 1 square, right? And then it will be 1 by 1 minus n square by 2 square and 1 by 1 minus n square by 3 square and so on. And this will go on till where? The last term will be basically 1 by 1 minus n square by alpha square, right? Great. So now this should remind you of the infinite product of the sine y by y that we had already gotten earlier, right? So I will write this result on the next screen. What I'm getting here is n factorial into minus n factorial is equal to 1 by product, infinite product of k goes from 1 to infinity, 1 minus n square by k square, right? Great. Now we have already seen sine y is equal to y times product k goes from 1 to infinity 1 minus y square by k square pi square, right? So I want to connect these two formulas like Euler did, right? We have this result, we have this result. So if we set y to be equal to n pi, right? We set y is equal to n pi in this equation. We get sine of n pi is equal to n pi. Product of k goes from 1 to infinity. We are getting 1 minus n square pi square by k square pi square, right? Pi square gets cancelled and we get basically n pi. Product of k goes from 1 to infinity 1 minus n square by k square, right? And notice that this product is here, right? So we have this infinite product and this infinite product is equal to sine n pi by n pi, right? If I take this n pi here, right? So now we are getting this wonderful result. This is equal to 1 by sine n pi by n pi, right? We are getting basically n pi by sine n pi, right? Is equal to n factorial into minus n factorial, correct? Now this is amazing because now this makes sense even if n is not an integer. So we have this result n factorial minus n factorial is equal to n pi by sine n pi. And let's see what values we are getting. If I put n is equal to half, right? N is equal to half, I'll get half factorial minus half factorial is equal to pi by 2 sine of pi by 2, right? That is pi by 2. And that because we already know minus half factorial was basically for us root pi, right? We had derived that as root pi earlier in the video. So we have half factorial is equal to root pi into pi by 2. Therefore, half factorial is coming as root pi by 2. So we are able to derive half factorial, and things like this using this formula. So finally, what is the final equation that we can write as a conclusion to the entire video? We can say n tau of 1 minus n is equal to n factorial minus n factorial is equal to n pi by sine n pi. That is the conclusion for this video. And basically, this all was done by Euler and in the 1700s. So it is astonishing what he had figured out. We have also found in the video values of half factorial, which came out to be for us root pi by 2. And we also found minus half factorial, and that was root pi. And basically, some factorial values like this are now obvious from this formula. This is called the reflection formula. And hopefully, this video will show you what is possible with intelligent application of the Taylor series formulas and some amazing creativity on the part of mathematicians like Euler. So hopefully that this will help you. I will put a link to Michael Penn's video on the Euler-Mascheroni's constant in the description for this video. And that video should also help you understand the details of the harmonic series and the approximation of that with the log function. Hopefully you like the video. Please subscribe to the channel and share the word. I'll be back with you with new content soon. That's it for now.